We're here today to talk about surveying and mapping with drones. This is a talk that I gave recently at the Stratus conference at RIT in Rochester in June 2023. And I like to start technology conversations with this graphic. This is the Gartner hype curve. And typically when we come across people at the beginning of their investigation into using new technology, they're somewhere here on the curve. They're getting excited about it. They're looking at all the potential and all the possibilities. And then we end up, finding them trying to struggle through the trough of disillusionment. I have a saying where sometimes you can characterize it that it's going to cost more, take longer, and be harder than you think. So we are pulling people up out of the trough of disillusionment onto the slope of enlightenment so that they can achieve productivity out on the plateau of productivity. So here's 5 things you need to know about UAV data accuracy. The first is that the truth is unknowable. We think we can measure things accurately, but the truth is we don't really know exactly where things are. There's always error associated with every measurement we make. What we want to do is become enlightened about how that works, right? And then be able to talk about that with our clients and with our team so that we can all have confidence in the authoritative accuracy of our data. Using a simplified example, something that everybody's somewhat familiar with, right? We can use the example of pi. It's the ratio of a diameter to a circumference of a circle, right? So if we were to draw a circle and cut a string and start to figure out that ratio, we'd immediately come up with a number of around 3. And then as we become more accurate in terms of how we make our measurements, we get more and more accurate and more precise in terms of how many significant figures we can calculate that out to, until we reach this sort of oh shit moment where we're like, okay, we can measure extremely precisely, but how much of that do we really need to know, right? What is the accuracy of our data? So we can measure a point at the center of this. What is this? This is an error ellipsoid. So if we can measure the point at the center extremely precisely, right, what's the error associated with that measurement? So it doesn't matter if it's got 2, 6, 60, or 600 significant figures on the end of that measurement. We still need to know what the error is in terms of where it actually is. So that's where the error ellipsoid comes in. Right? We also need to be talking about error in the same way so that we're all, when we use that term, we all understand what that means, right? Traditionally, we're talking about a measurement. This is mapping and surveying, a measurement that's compared to some known truth, right? Of course, we don't know what the truth is. So we're really talking about one measurement compared to another measurement. The difference between those 2 measurements is the error, right? Or the difference between our measurement and some known reference. If we have a known reference that we can all agree is the truth or close enough to the truth that we can use it, then we can compare our measurements against that and get an estimate of the error of our own measurements. Right. So here's a simplified graphic of a hill slope, and we can understand that there's some vertical error associated with our measurements that are defined by these red lines, which means that the ground surface is somewhere in between the 2 black bars. Same with horizontal measurement. We know that there's some horizontal measurement, horizontal error associated here. And that allows us to say, well, our horizontal position is somewhere within these black bars. And then we know that if we're measuring on a sloped surface, that horizontal error actually leads to vertical error. So where exactly is it? Where exactly are our points? And that brings us to thing number 2, which that there are standards. In 2014, the American Society for Photogrammetry and Remote Sensing, or ASPRS, compiled a comprehensive set of positional accuracy standards for geospatial data. Immediately following, all federal agencies and industry groups agreed to follow these standards. These standards give very specific guidance on horizontal accuracy for things like digital imagery, horizontal accuracy for derived data, such as planimetrics, and vertical accuracy for topographic data, either from LiDAR or photogrammetry. Then in 2023, early in 2023, that same group offered an update. So we now have edition 2 of the ASPRS positional accuracy standards that updated the 2014 standards. Now, a couple of noteworthy things about the new 2023 standards, right? We've eliminated the use of the 95% confidence interval. We found that using the 95% confidence interval and the root mean square error, RMSE, those are two statistical calculations that essentially measure the same error and the same data, but they're reported differently. And because they're reported differently, it was causing some confusion as to do I use this number or do I use that number when they're effectively talking about the same error in the same data set. So they've suggested that we stop using the 95% confidence interval and standardize on the RMSE error instead. Another previous rule was that if we're going to use checkpoints or reference data, that those checkpoints or reference data have to be of a much higher quality, much higher accuracy than the data we're trying to test. So that's where the 3 times rule, they had to be 3 times or better than the data we're trying to test. Because the data we're collecting now with modern sensors and drones is so high, accurate, and so precise, it's very difficult to achieve that standard. And so they decided to do away with it. But in so doing, that means we can no longer ignore the error that's associated with our checkpoints. So we need to understand the error of our checkpoints and understand the error of the data we're capturing. A couple of other highlights of the new standards. The number of checkpoints previously was recommended at 20. So we needed a minimum of 20 checkpoints to make an authoritative statement about our data. And why was that? The reason was because if you throw one of those points out, because it's a bad point for some reason, you still have 95% of your points, and you can make a 95% confidence interval statistical statement. Since we're doing away with the 95% confidence interval, they're recommending that we increase the number of checkpoints to 30 to meet a more rigorous statistical standard when trying to make authoritative statements about the accuracy of our data. The new standards also add a new terminology in trying to move away from talking about vertical error and horizontal error in the X and the Y planes, and talking now about 3D accuracy, 3D positional accuracy. So stay tuned and expect there to be some more discussion about this. And one of the nice things about the new standards is that they come with an addendum that is a general guidelines and best practices. So the idea is that as technology changes, the guidelines and best practices can be adapted to new technology without necessarily having to go back and change the standards for the data. So now that we know that there's standards, do they apply to me? If your data that you're collecting, whether it's with your drone or with your phone or with any other sensor technology that you have, if the geospatial positioning in that data is important for the use and the quality and the accuracy of that data, particularly if you need to report the accuracy of it, then the data is geospatial, and yes, these standards apply to you. If none of that is important, if you're just flying video or if you're just taking pictures, then the standards don't apply. Who cares? That brings us to item number 3. The first thing, the truth is non-knowable. The second thing, there are standards. What the standards tell us is this item number 3, you must test the data. You can't make an authoritative statement or definitive statement about the accuracy of your data if you have not tested it. You can't just buy a piece of equipment, read the manufacturer's specifications and say, the manufacturer specifications give me this error statement, therefore that error statement applies to my data. You can't do that. You can't go out and collect data with that piece of equipment, run it through a piece of software, have the software generate an error report and say, well, my software told me that this is what the error is. You can't do that either. There are specific guidelines that tell you that you must test and how you must test. So for example, if we have an area on the ground, this is kind of a cartoon area on the ground that might represent a particular property or area of interest that we want to map. Right. The first thing we do when we're collecting drone data is we come up with a flight plan. And that flight plan, we want to make sure it has proper overlap, proper crossings, and that has good control. The control allows us to anchor those points to the ground so that we can make accurate measurements based on the surface of the Earth. Once we've done that, we need to separately go out and collect checkpoints. These checkpoints are not used in the processing of the data. They technically are independent and have nothing to do with the data capture and processing of the data. And so there's very specific guidelines now in the ASPR standards about how many checkpoints, where they need to be, and how far apart they should be, things of that nature. So, for example, right, the standards used to say 20 checkpoints. Now we need 30. We don't want to collect checkpoints on sloped terrain. We want to make sure that they're on as flat of terrain as possible. Anytime that there's a slope, we know that that slope introduces some error. So we want to try to, if we're measuring accuracy, we want to try to measure accuracy on the flattest parts of the project as possible. We want to do it in open areas where there's no vegetation. Vegetation also introduces error. So we want to make sure that we measure our checkpoints away from vegetation. And there's some guidance on how far apart these points should be located from each other. If we cluster all the points together in one spot, then they're not effectively measuring accuracy of our entire data collection. And we need to distribute those points evenly across the project site. In addition, the ASPRS standards give a specific addendum for guidance on collecting both ground control and checkpoints. So if you're not sure what to do, you can refer to the guidance on how to collect checkpoints. So let's say we've read the standards now, right? We've gone out and we've collected a bunch of checkpoints so that we can conduct our test and we can conduct our accuracy test. So we have our checkpoints. What do we do next? That brings us to item number 4. Know what the error statistics are. In this case, the root mean square error. Can't tell you how many times I have actually had conversations with licensed surveyors and licensed engineers and PhDs who haven't taken the time to understand what RMSE actually is. One way to know what any specific thing is to first get at what it isn't, right? What RMSE is not is an upper or absolute limit. So if there's an RMSE of 2 inches, that does not mean that that's the upper limit of error and that there are no measurements that have error exceeding 2 inches. That's not what it means. RMSE is not the average. We don't take all 30 points and just take the average of the error. That's not RMSE either. And it's not plus or minus. Plus or minus, if our target is a certain error, say plus or minus 2 inches, that is not what RMSE is either. So anytime that you are having a conversation or the conversation tends toward the use of these types of terms, you should throw up a red flag and make sure that everybody is on the same page in terms of what we're talking about with respect to error. What RMSE requires is that somebody goes out and measures reference data at the highest accuracy possible. Previously, it was 3 times higher than what the standards are for your project. Now, the guidance is just make it the best possible data and make sure you're trying to track the error in your reference data. But either you collect this or somebody else collects it. It doesn't matter, but somebody has to independently go out and measure reference data. This is not data you can pull off of a CAD drawing, which I have seen done. It's not data that you can pull off of a Google Earth image, which I have seen done. And it's not data that you can go out and just capture with your phone or your Android, which I have also seen done. So if you're not sure about what you're doing with respect to the measurement of reference data, it's possibly time that you bring in a licensed professional to help. Right. RMSE requires that you not only go out and collect the 30 checkpoints, but that you then compare the measurements that you made in the field to those corresponding measurements coming off of the data that you've collected using your drone or your other sensors, right? And then you compute the difference, right? Measurement 1 versus measurement 2. Measurement 2 in this case would be our checkpoints, right? So now we've got a whole bunch of differences. We square each of those results, we compute the mean of all of those squares, and then we take the square root. So in a simplified version, here's this Excel spreadsheet, right? You put all your 30 points in there. In this case, this is a vertical accuracy that we're doing, and the circle above is the formula that you can punch right into Excel. Now, a lot of processing software will do this for you, It'll allow you to upload your checkpoints and it will calculate an RMSE error for you. But there, you can always do it manually as a check independently in a table with something like this. So this spreadsheet is actually on our website, on our resources page. If you want to go download it and play around with it, you can. And at the bottom here, you see you calculate or report your total RMSE error, your root mean square error. The ASPRS standards require you to report the error in centimeters, because then that corresponds to specific accuracy classes, which then have authoritative definitions associated with them. So you see in this case, the data that I was testing came out to 6.37 or roughly 6.4 centimeters, which is good enough to meet the 10 centimeter accuracy class, if that was the goal of the project. Right? So what do these RMSEs get us? They bring us back to our friend, the error ellipsoid, right? They start to then begin to help us define how big this error ellipsoid is. So our goal is to make this as small as possible. And that brings us to the last thing in the 5 things you need to know about UAV data accuracy. The data accuracy is not just a function of the camera or the LiDAR sensor or the GPS system integrated into your UAV. The accuracy is a combination of the entire system. And that entire system includes the human element. In some cases, the quality of the piloting can affect the accuracy of the data, the amount of overlap that you put into your flight planning, the speed at which you fly, the timing of the triggering of the camera or the sensor, the quality of your control can affect the processing and the accuracy of the data. So even things that are out of your control, like the weather and or the time of day that you fly, shadows can influence the accuracy and the ultimate quality of the data. Bad weather can influence the accuracy and the quality of the data. Or even the targets that you use. If you can't definitively locate the center measurement point of that target that was used to measure that reference point within 2 pixels, that's going to influence your ability to make an authoritative statement about the accuracy. You might go out on a perfect day and collect perfect data, and the data is incredibly good. But if you use shitty targets, you're not going to be able to find the center point, the measurement point of that target within enough pixels to then be able to make a definitive statement about the accuracy of that data. So you need to, the quality of the targets you use can actually impact how well you can calculate the accuracy of your data. So it's in the entire system. It's not just the manufacturer's specifications on the camera or the manufacturer's specifications stated by the drone manufacturer. So those are the 5 things you need to know. If you want to shoot me an email, you can, or if you head to our website, you can find additional resources like this video and some other things, and we'll see you out there flying.